So welcome to the HPC Best Practices webinar for September. Today we're going to hear about the application of the OpenSSF Best Practices program to scientific software. Our presenters are going to be Ross Bartlett from Sandia National Labs, Yanfei from Argonne, and Pratik Nayak from the Technical University of Munich. And just so people understand a bit how this is structured, Ross will be the primary speaker, and he'll be just giving an overview of the badging practices and how they work and what the expectations are. And Yanfei and Pratik will have some short discussion of their experience as scientific software developers getting the badging for their projects. And hopefully at the end, we'll have ample opportunity for questions and answers of anybody involved, but I'm hoping that Yanfei and Pratik will particularly elicit some questions and discussion. So we prefer to use this Google Doc, and I will put the link into the chat again, but it's here on the screen. For the Q&A, please put your questions there. If we don't have time to answer them during the webinar, we'll get our speakers to write out some answers afterwards, and they'll be part of the archives that are made available. And we also ask you to give us some feedback on the webinar. This is a very short, like 3-question survey and has a box for comments as well. And finally, like all of our webinars, this one will be recorded and will be published. Everybody who registered will get a note when the archives are up so that you can share it with your friends and colleagues who might have missed it. And you can go back and review it if you want. So with that, I'm going to stop sharing and turn it over to Ross.
Excellent. Thank you, David. Okay, so let's get into it. The application of the OpenSSF Best Practices badge program to scientific software. Okay, here we go. All right, so first thing is, a couple years ago, I wrote an article for the Better Scientific Software site about
Ross, you're not sharing.
Oh, shoot. Sorry about that. Thank you for that.
There we go.
See it okay? Gotcha. Thank you. Thanks for the reminder, David. Yeah, so a couple years ago, I wrote an article for the Better Scientific Software site that has a lot of the same information and overviews and perspective that I'm going to give as part of this talk. So you can read that in prose form. Okay, so so just in general, security issues in open source software is becoming a larger problem. There was this kind of famous heartbleed bug back in OpenSSL in 2014, which is still generating news articles 11 years later. You could argue is one of the big motivations for something like the OpenSSF for the open source community. But yet we're in computational science, right? So, or in HPC. But you can still argue there's a lot of different use cases and so forth where software vulnerabilities are a problem even in our domain. And I would argue that as we are incorporating AI agents into our workflows, which we're going to have to do in the next few years, we're all going to be impacted by this. We're all going to need to know a lot more about security because it's like the wild west right now with these things. So one of the S's in the OpenSSF stands for security. It's a foundation that was formed by the Linux Foundation to really bring up the quality of the open source ecosystem that a lot of us build on top of, and has all the major players that are contributing to it as major funders and contributors and so forth. Trying to make it so that open source software is developed securely from the very beginning. So just a brief overview of it. What are these practices? So these are a set of best practices that are curated from the open source community that have very specific actionable criteria which require supporting evidence. So unlike other efforts that I've seen that are kind of high level and nebulous, these are very specific. It can be very clear whether or not you've met them or not in most cases in a more objective way. Now there is a particularly strong focus on software security, which addresses a lot of the more recent US federal government notices about software security that a lot of us are aware of. But I would note that most of these best practices are applicable to all software, not just security critical software. One of the really nice things about this program is that there's this badge app site, which used to display the practices and expanded descriptions, and your project can put in your own entry for it, describing how you are interacting with these best practices and using them or not using them, and explaining that. And this generates a badge that you can put on your project's hosting site that can show everyone that you're participating in this program and sort of where you are in your journey to achieve a badge and go beyond just the basic passing badge. It's also, you could argue, a pretty good learning tool for best practices for developers and projects. It's used as a roadmap for continual improvement as your project incrementally adopts better practices and improves your scores in different areas. You can also use it as a standard index into a project to see how it handles different kinds of processes. And finally, you can use this as a website template for having customized best practices inside of your organization. They've actually did that last year at Sandia Labs. They took the site and they cloned it and they modified it and created some customized practices inside of Sandia. Okay, so do an overview here. So the basic structures of the practices are this. There's 3 different levels. There's passing, silver, and gold, and various numbers of different must, should, or suggested in each area. And the practices are broken down into 6 different categories, one of which is security. And each of those categories is broken down into subcategories. So for example, here on the right, for example, we've got at the passing level, we have the set of basic practices and then the subcategory of basic project website. So each, and then it will describe whether or not the practice is required at that level, some detail on what it takes to satisfy it. And sometimes there's like a URL that you can put in that'll be validated in some cases, and other text fields you can put in. And every practice has a unique short name linked to it, so you can unambiguously refer to the practice. So here's an example of some practices at the passing level in a few different categories. Won't go through all these here, but you see some of them have like a URL you need to fill in. Most of them have a text field that you can put in to describe it. So nothing here should be terribly surprising. Another example, things like bug reporting, must, required, should, vulnerability reports. You gotta have a working build system. You gotta have an automated test suite. And if you add new functionality, you should have tests for that. I think that's great. Another sampling here. So under security, they got several of those. One I'm going to spend quite a bit of time on later talking about is this area of secure development knowledge. Kind of unique from the other practices a little bit. And then, of course, static code analysis and so on and so forth here. And if you look through a lot of these things are not specific to just software security. Most of them are applicable to almost every project, I would argue. At least projects that want to serve their customers and be correct. So here's some breakdown of the practices in terms of the statistics of numbers, number of must, should, and suggested at each level, the subset of those that are security specific, those that can be marked as not applicable, numbers that require justification and or a URL. Some observations about this. Some of the practices are relisted at higher levels, going like from suggested or should to should or required. For example, the bus factor is a should practice at the silver level, which is relisted as must at the gold level. Meaning you have more than one person who's a primary contributor to the project. Again, most of these practices are not specific to security. And even the ones that are security specific, most of those can be marked as not applicable, except I think some of the hardest ones, which again, I'll talk about later. So most HPC projects don't have these practices don't apply to them because we're not doing things like cryptography and user management and so forth. Okay, so let's talk about the badge app site, which is one of the better parts of this program. So here's a badge app site snapshot from a few days ago. So there are currently 8,900 projects on there. The first one is the badge app itself, created by David Wheeler for this project itself. So you can use that as kind of a guide for how to follow the practice and fill it in by the people that actually created these set of practices in the site. And if you look through here, you'll find like almost all the really major pieces of open source software that we build our ecosystem on for open source. As of that snapshot, there were 56 gold level projects, so you can search based on different levels and so forth. You'll see them there. Thank goodness the Linux kernel's on there, eh? All right. So one thing we see with this is that this was put into place back in 2016, and growth has just been steadily accelerating over the years, and that continues. So it's a well-accepted and well-adopted badge program and site. And the projects themselves have been very static over the years. They really have not changed, which I think is a really good testament to the fact that they did a good job of putting those together, I think. So here's a breakdown in terms of those 8,900 projects, how many are passing, about 11%. And then, about 10% of those go on to silver, and then, about half of those go on to gold. So, yeah, there's not a lot of gold projects out of that. So here's an example of what the badge app site looks like for a project. So I created one for a piece of code that I wrote years ago called Tribbit's Core. And I went through the process, and I think I did a good faith effort to satisfy all the required practices. There was one that I could not in good faith mark as being satisfied. So I only have 99% on this, and I'll talk about which practice that was and why it's so difficult, and something that we need to deal with in terms of our community if we're going to adopt this set of best practices for our codes. So for example, inside your project, in your project entry, you'll specify whether the practice is met or not met, release notes, and you put in a URL. In fact, it'll go and search automatically and see that those URLs exist and tell you if they don't. You can post the badge on your project posting page, like on GitHub or GitLab or wherever. Works with markdown files and restructured text and other things here too. So it creates a nice little badge that you can advertise that you're participating in the program and sort of where you are in your effort to achieve the badge. Okay, let's talk about some other benefits of the badge program. Okay, one is I think it's actually a pretty effective learning tool for a lot of people. So there's a page on there that lists out all the practices, and you can expand it with additional details and rationale, and read through that. So I mean, there's 129 total best practices, and it takes quite a while just to read through all of that. And depending on your level of familiarity with these topics, you can spend a lot longer just clicking on things and so forth. I mean, I remember I learned quite a bit from coming through this. So yeah, that's that. Okay, for example, this is an example of a breakdown of one of the practices, open source software. So it goes into some detail about open source software, some acceptable licenses, what some of the issues are, the rationale, and so forth. So you can learn a lot about open source software, for example, and licensing from that. Some recent things that I learned actually from this that I didn't know before. You can see a lot of the detail about these practices actually in the badge app itself for your project. Things like you can click on show details, and it goes into a lot of the same detail here. So it's very accessible in different views. You can use this as a way to keep track of continuous improvement. You can kind of see where your project currently has gaps and missing. So for example, you can click on expand panels and hide met or not applicable. And that will show you just those practices that you're not currently meeting. And also the site will send out periodic email reminders like every 6 months or something, just kind of encourage you to keep making progress on your project. This is what it looks like for one of the practices where it's not met. So you see I marked it as unmet, and I gave my justification for it, but it's just a suggested practice at this level, so you don't have to actually do it to get a passing level badge, but you do need to justify why you don't meet it. I think that's reasonable. It's not a big deal. All right, this is the one where Tribbit's failed on, where I could not in good conscience click met on this topic, this idea of that the project has to be one developer that knows how to design secure software. So I'll talk about that a little bit later in terms of what the criteria for that is. But yeah. Another thing is it provides a standard index into a project. Like I know there's a bug reporting entry. So in case that's not clear on the project's website, you can go here and have a very unambiguous link to how the project manages their bug reporting process. Or I know that gold level projects have to have documentation about their internal implementation. That's how I found out about the implementation for the badge app site itself. It had really good documentation for it, and I found it easily because I knew there was an entry for it. I knew that it was required at the gold level. Okay, so let's talk about software security practices and some of the more challenging parts of this, I think, for at least for our community, I think, or even for a lot of communities, I would guess. So what's interesting about this, again, I think like OpenSSL and the Heartbleed bug was a big motivator for the OpenSSF, kind of a wake-up call for the open source community. So they actually had 2 entries for OpenSSL, one before this site, or at the time of the Heartbleed bug, and then afterwards. So they got a passing badge now. But if you look at their entry before Heartbleed, they were only 63%, and the practices that they did not follow were a little bit frightening. But yeah, so there you go. Okay, let's talk about the security focus of these practices here. Again, 16 of the 67 passing level practices are related to security. 9 of those can be marked not applicable, and similar subsets for the silver and gold level. Until recently, software security, I don't know what you define recently. I mean, I've been around a while, but, kind of classic books on software engineering had almost no mention of software security. Like this massive book, Code Complete, 2nd edition, one of my favorite books on software engineering. It's over 800 pages in 2004, and it had exactly 1 paragraph that talked about software security, literally, in the entire book. More recently, the 20th anniversary version of the Pragmatic Programmer had at least 7 pages devoted to the topic of security. That's something, at least. But my view is that a lot of us are going to have to really increase our awareness and visibility of software security due to issues of AI agents and large language models and so forth. So I think that's going to be a much bigger issue for us going forward, because none of us are going to be able to completely ignore that in the future. So this comes back to the most difficult practices, in my view, to get a passing grade for most of these, and which is where my project failed, because I couldn't in good conscience answer yes to no secure software. I did mark okay for the next one about the common kinds of errors for the kind of software that I have. But so what does it mean to know secure software? Another thing to note here is that if you go through all these 129 practices, these are the only ones that are not actually something that you do or a process that you have to follow. Or this is just like, hey, do you know what you're doing? But these are the only 2 ones that fall into that category, which is kind of interesting. All right, let's talk about no secure design. So why did I not click OK on this? Because, they talk about some general issues. A lot of these things I was aware of. A lot of them, I don't have a security background. And then they mention these courses. The shortest course that is mentioned and recommended here is this free OpenSSF course, and it's 18 hours of work every 2 years. That's the least consuming option. The other ones are much more time-consuming efforts. Is that reasonable for us? I don't know. Let's talk about that in a minute here. And then another one is no common kinds of errors. Okay, we've got classic errors like classic buffer overflow. Those are huge classification of problems. Let's talk about that. So there's this, common security vulnerabilities, or CWE list that comes out every year, the top 25 vulnerabilities that are reported. And 11 out of the top 25 do relate to CSC and HPC software in some respect. And 5 of those 25 are incredibly common in all of our C, C++, Fortran, CUDA, whatever codes, right? Classic reading and writing out of bounds, pointer problems, integer overflow, and so forth. But these are also things that impact the basic correctness of our software. So you can't really argue that you have a correct piece of computational software if your software is doing these sort of things. So in this sense, software correctness and quality and the really basics of software security are really best friends and kind of are not antagonistic at all. Okay, so there is this really challenging burden of what do we do about this? Okay, well, so this one here of So again, a lot of these practices about security can be marked as not applicable. Like there's a whole bunch of them that have to do with cryptographic algorithms and protocols. Well, most of our software doesn't have that. So I marked not applicable on all of those, and probably a lot of us will. But again, this is big one of the project has to have at least one developer who knows how to design secure software. So the current criteria for that, I think, is too onerous for most computational projects. So I think as a community, we can decide what this means for us in terms of secure software. I'm kind of like brainstorming some ideas, like maybe you have 3 levels, kind of day-to-day computational software developers that just need to know how to not have buffer overflows and stuff like that. Things that you can solve with like modern languages and like modern C++ and the C++ coding guidelines can eliminate most of those things. Maybe that's like 4 hours every 5 years or something. I don't know. And then level 2, people that are doing like HPC DevOps software, getting a little more issues where there's some security issues. Maybe that's 10 hours every 3 years or something. And then people that are doing like, real system software, user management, anyone doing anything with containers in our community, and there's a lot of that going on, those people really need to be taking these courses and really know this stuff forward and backward, I think. But that's not all of us. That's a very small percentage of us here that I would put into the bucket of HPC. All right, so that's it for that. So I'm going to hand this over to Pratik to talk about Ginkgo.
Thank you, Roscoe. I just basically wanted to give a very quick overview of one of the software projects that maybe is interesting to the audience here, and it's called Ginkgo. Next slide, please.
Oh, here we go.
Yeah, so Ginkgo is basically a high-performance numerical linear algebra library. So I would categorize it in the level 1 software that Roscoe mentioned. It's a modern open source modern C++ software with a focus on comprehensive unit tests, having benchmarks, particularly because we are at the middleware level, which basically lies between the vendor provided software and the applications such as some scientific simulations and so on. So it's heavily focused on having a user-friendly interface, and particularly because our users, our application writers, they are mostly concerned about physics. We want to have an integration that enables them to have to get them prototyping and writing production level software very fast. And on the other end, we also want them to have good performance. So we have support for various hardware backends, in particular, the most popular ones, which are the GPUs of all the different major vendors, NVIDIA, AMD, and Intel. And from a portability point of view, we take a slightly different approach. We basically write kernels in the vendor native backend. So for example, for NVIDIA GPUs, we write in CUDA kernel, in CUDA software, for AMD in HIP, and Intel with SIG. And to ensure our software can also take advantage of the multi-core CPUs, we use the OpenMP programming model for that. And we have a distributed support as well with MPI, which forms a layer, and each rank essentially can map to one of the executor, which can be NVIDIA GPU, multi-core CPU, or which of the other backends. So from the feature point of view, we have sparse matrices, Krylov solvers, preconditionals, which mostly form one of the major components of scientific simulations. In particular, for example, if you have libraries which do finite element simulations, fluid flow simulations, or for example, electrocardiophysiology simulations, in applications like MFEM, sundial, steel 2, and so on, they essentially have large-scale systems, linear systems that they need to solve, and we basically they basically offload those systems to us, and we solve it for them. Next slide, please. So the architecture of our software library looks something as shown in the figure here. We have a core which is mostly backend agnostic. So a user and the developer mostly develops algorithms and writes them without actually concerned about the hardware itself. And then you have kernels which are implemented across all the different backends. And these backends use the vendor native programming model to write high performance code, which works well on the separate backends. And we also have a reference backend, which has a single threaded implementation, which ensures that when we implement something on a high performance backend, such as CUDA or any of the other GPUs, that can be checked with that single thread implementation and ensures that the functionality is correct. And we focus on having unit tests and also a continuous integration pipeline to have things that are very robust. Next slide, please. We also ensure that our software is scalable, and here we just show a simple strong scaling on the Jupyter supercomputer, which is the large-scale supercomputer in Germany, and we get a good amount of scalability on up to about 1,000 or more GPUs. Next slide, please. From a functionality point of view, we have the basic functionality such as sparse matrix vector products, Karov solvers, preconditioners, some specific functionality for applications such as batch functionality, and also algebraic multigrid and sparse direct and so on. And with the focus on applications, we have some utilities which enable easy integration with different applications. Next slide, please. As Python has been a very popular sort of a domain-specific language in some sense, we have recently built a interface, our Python interface for Ginkgo, and in this slide you can basically see that we perform reasonably well compared to CuPy, PyTorch, and TensorFlow for the basic operations, and also showcase the performance of our software compared to CuPy. And the interface on the left side basically is like similar to NumPy, and it's sort of like a drop-in replacement for that. Next slide, please. So the journey of Ginkgo, or when Ginkgo started mostly around the exascale computing project effort. And during the exascale computing project, the main focus was having a lot of different mathematical softwares, application software, system software, and having the capability to actually integrate them and make them interoperable, right? So this basically led to the XSDK effort, which is the extreme scale software development toolkit. And the idea was that each software essentially follows a set of community package policies, some mandatory policies, and some recommended policies. And Ginkgo is essentially part of this XSDK effort, which basically was there with a sustainable software development strategy in mind. And for example, some of the policies were that each software needed to have a SPAC installation. SPAC was basically one of the main drivers of interoperability in XSDK and also in ECP, I think. Another thing was having a comprehensive test suite, ensuring platform portability, and having a person to contact to ensure that the interoperability was always existing. And naturally, there's also some recommended policies that encouraged software sustainability, extensibility, and also, in some sense, security of the software, such as file grind checks in CI/CD, or ensuring that the software provides a list of dependencies. Next slide, please. So basically, for Ginkgo, we achieved a passing badge. Essentially, I checked the list of things that were needed for the OpenSSF badge in the end of 2023 for our 1.7 release. And to note, we are at our 1.10 release. And that basically follows the same list that Roscoe mentioned. And you can have a look at the link for more details of the badge. Next slide, please. So regarding the different challenges for obtaining the badge, basic things such as having a Git repository, having version control, ensuring good reporting, and so on were very easy to obtain because they were mostly common practice. The quality aspects of the badge required some attention from us, but as we were part of XSDK, those things were also very straightforward for us because it meant that we already had a CMake build system, we already had comprehensive unit tests, We had a CI/CD set up, which already checked warnings and then ensured that everything was smooth from that point of view. The security point of view was the one that was slightly more involved for us, and similar to as Roscoe mentioned, the main reason was that we needed to check that design principles were being followed, and as a level 1 software, just following the nomenclature that Roscoe mentioned, some of the principles essentially were applicable for us, but many of them were only loosely applicable. I actually tried going through the OpenSSF training org and then taking the course. It provides a course, but the issues that I found, I guess also there's some discussion in the chat there, but only some topics were essentially relevant for us. But what we did was we ended up taking selectively part of the course that were relevant for us. For example, I think HPC software, it's still important to have good input validation, error handling, having code scanners and code analysis tools and so on. So that was quite useful for us in general, I think. Next slide, please. So as Roscoe mentioned, basically the badge also provides some different extensions, essentially the silver and gold criteria, and surprisingly, Ginkgo actually fulfilled most of them. For example, we already had static analysis in our CI, dynamic analysis such as Vagrant checks, memory leaks, address sanitizer, thread sanitizer, and so on. We also had very specific coding standards, ensure that code is uniform across different developers, and we have very good sort of copyright requirements, which follows the general copyright guidelines set forth by OpenSSF. But we don't actually currently follow all of our paths, in particular the upgrade paths, supporting older versions of our product for a long time, which is slightly difficult with the lower number of developers that we have in usual HPC codes. Next slide, please. So in general, I think the benefit of the badge is that in most cases, security issues are also usability and performance issues. So out-of-bound reads, writes, memory leaks are very common in HPC software. And if you do conscious checks when you are actually trying to obtain this badge, then you can ensure that you identify the issues and then rectify them. In particular, if you manage to have static and dynamic analysis in your software or in your CI, then it also makes you identify and fix performance and usability issues much earlier and probably reduces technical debt in your software code base as well. Next slide, please. So so many HPC codes are still written in C++, and they always tend to have a high number of security vulnerabilities, I guess. But that might not be critical in the sense of from a security point of view, but still I think it's useful from a usability and performance point of view. And from the OpenSSF badge point of view, I think the basic requirements for security software ensures that it kind of builds a little bit of trust in users, and it shows that users, different things are kind of satisfied. From an industry standardization point of view, it makes this software more sustainable. And of course, because we are all mostly dependent on public grants and funding, I believe that this badge can also be advertised when applying for grants and funding, and also makes maybe the reviewers more willing to give funding to a software which maybe follows some general good practices. Yeah, and that's mostly it from my side. So thank you for listening.
All right, thanks. All right, we'll move on to Yanfei and MPICH.
Right, thanks. Hi, I'm Yanfei Guo. I'm a computer scientist at Argonne National Lab. I'm a co-developer of the MPICH library. So I'm going to talk about our experience regarding the OpenSSF best practice in the MPICH project. Next, please. So MPICH itself, it's a long-running software project that essentially we're the first and most comprehensive implementation of the MPI standard. This project has been run by Argonne for more than 30 years, and And we have been a open source project since beginning. And because of that, there's many vendor partners that collaborate with us and use our software as the base of their own MPI library. Because of that, MPICH and its derived MPI libraries today are being used on 7 of the top 10 supercomputers. And the code base right now is actually not the biggest in history, but it's still huge. It has more than 650,000 lines of code, mostly regular C code, and there's also like 50,000 of Fortran code in there. So it's a fairly big code base. Next slide, please. So a lot of the modernization of the project has been happened during the ECP years, and so right now our source code is hosted on GitHub instead of internal Git server, and we have all the libraries and dependencies shipped with the source code as well, and we manage issues, pull request development activities through the GitHubs. And also provide the wiki and information on GitHub. And in addition to that, we still have our self-host website and our legacy mailing list for discussion. So that these changes have basically helped satisfy the basic requirements for getting the badge here. And in addition to that, one significant thing we did in the past decade is related to the testing, which I'm going to go into details about. We have our own Jenkins system that we manage, and we have our own test bed for testing. And in addition to that, we work with Argonne Leadership Computing Facility (LCF) to use their CIs in order to just test our code directly on the big machines. Next slide, please. So a typical development cycle in MPICH basically starts when a developer creates a pull request to on our GitHub, and once that is started, there's a bunch of tasks like the warning and white spacing and authorship checking are automatically kicked off by GitHub. And the one interesting here is the authorship, because our license requires all the code contributed, all the contributors sign a contributor license agreement. So we'll basically just check all the authors against whether they have an agreement. So make sure that we're compliant on the license front. And once that is done, usually a set of functionality tests will be triggered manually. This is mostly depending on what communication library that the code is touching, and whether it's using GPU or a special kind of compiler need to be used. And once those tests pass, the PR is going to be merged, and that would in turn update the main branch, which is our development branch. And then our CI system would pick up those changes and trigger a more comprehensive set of tests nightly. So one of the interesting things related to this is the best practice badge does require the testing to have a strict option, which is in our case is using the warning flag and also embedded in other test configurations. Next slide, please. So the testing is a huge task in MPICH because we have our own test suite and has more than 3,000 test jobs, and we're also using benchmarks. And the task code here itself, it's more than 160,000 lines, and we're doing the automated test would validate and test our code against different compilers and different system images. So our experience basically tells that if you have enough different combinations, sometimes even the weirdest problem might get caught in one of these system. Sometimes the FreeBSD is helping us a lot to figure out some weird condition for failure. Next slide, please. So this is our Jenkins CI. We have, like I mentioned, we have many different task configurations. So each of these tasks named here is actually a series of task configurations. Basically, you have, for example, different library and different compiler. All these are we basically run different combinations. So our nightly tasks usually takes 10 to 12 hours to finish. So we usually just trigger them at midnight and check the result in the morning. And one thing we did differently is that we're not directly using the GitHub action or workflow to run a test. We use a GitHub hook that connects GitHub and our Jenkins server, so we can just go to any of the PR and add a comments like this, test MPICH CH for most. That will in turn trigger the test jobs on Jenkins. On our Jenkins server. And as you can see, if any of these tasks is not clear, you can't merge. The merging is blocked unless overridden. Next slide, please. So the unique challenge, I think, in testing HPC software and in order to, if you're looking at to meet the badge requirement, I think for HPC software, a lot of the case you do need HPC hardware to test. Like we're communication library, so we want to test against InfiniBand, against Craze networks. So those are not available outside the lab, generally speaking. That is why we have to host our own testing cluster and self-host the Jenkins CI, and that is not the way I would recommend anyone to do, because for us it took 10 years to figure out, and after 3 major revisions to get this thing done correctly and efficiently and automate most of the thing. Next slide, please. Like Ross mentioned, the meeting security requirement is kind of an interesting situation, especially for the HPC software. So in our team, so me and another developer, we did the course, the LFD 1-to-1 course, which gives you a sufficient information of what developing secure software like. For our case, it's in actually practice, it's actually simpler, because most of these courses and security practice are targeting directly user-facing services or software in an untrusted environment, like you open up a service on the internet. And most of the HPC application actually runs in a much more controlled environment, which if you look at the course, it's considered as a trusted environment. So that's different kind of requirement and different scenario. And since we don't use crypto, and we don't have any need of crypto, so a lot of this requirement on cryptographic is not applied to us. And then so for MPICH, basically, and for many of the software project, I think the one thing you want to make sure is having a secure delivery of your software. So we have HTTPS for our own website, which Argonne security also requires us to do that. And I imagine your institution probably have the same thing. And also the code repo should not leak private credentials. So this is you can have the different tools that you can check that. Next slide, please. So if you do the LFD 1-to-1 course, there's a huge section just mentioned, just talking about how different analysis tool, especially dynamic analysis tool, can help mitigating some of the security issue. So we do those. We do both static analysis and then dynamic analysis as part of the testing configuration in MPICH. So our nightly test has those. We initially do this not because of security, but just to improve the quality of the code, because MPICH being a very old software, some of the code are written by students and postdocs, and may or may not be at its best quality or hardened for a large deployment. And since our vendor partners is relying on our software code, so we constantly try to find new ways to improve the quality of the software itself, which is why over the year we adopted tools like Coverity that does static analysis, and also CLAN, address sanitizer and the UB sanitizer. Now, so if you have a software project like MPICH that's maybe 10, 20 years ago and never done this before, you be aware that the initial barrier of using this tool might be quite high, because for example, the static analysis Coverity, we usually one report is going to have a few thousand of different kind of issues based on static analysis. Some of those are false positive, but because there's so many of them, it's really hard to parse through. What changed the situation is when we start use address sanitizer and the UBSAN, and we just took a period of time just looking at all the warnings and in the strict build, and the entire team just fixing those. That's putting all the other development work aside, just focus on this and get this clean up. Once that is cleaned up, keeping it clean and maintaining it is much easier, because every time you change the code, if there's anything wrong, the tool can report to you. But initial cost is fairly high. Next slide, please. So I would say in MPICH's case, getting the badge is sort of easy, because by the time I'm looking at the requirement, we already done most of the thing, including the analytics tools. The one single challenge is probably on the security and how to maintain the developer that knows how to write secure software. I would hope that there's maybe a more lightweight courses and tailored more towards to HPC software, and that would significantly reduce the barrier of getting the badge, and would help promoting these software safety security practice to more HPC software. So that's all the slides I have, I think. Thanks.
Yep. All right, thank you. All right, I'll go to the last final slide here. So just in summary, just to reiterate, so the best practices, a badge program, are a set of actionable collection of the open source community's best practices. That's a lot of best practices in it. But it's got this badge app site that codifies a lot of these practices and provides links to fill it in. And there's a lot of automation in terms of checking URLs and so forth. It actually can fill in a lot of things for you automatically when you first create it. Like if you have a project on GitHub, you can just point to the GitHub project and it'll fill in a lot of things automatically if you're using sort of the standard file names for things like license and README and contributions.md and so forth. Again, you can display the badge on your project's hosting site to show that you're following best practices and where you are in that journey. It contains features to help you identify areas of improvement and sends regular reminders, and makes it easy to kind of see where you could be improving incrementally over time. It does provide the foundation for customized best practices sites inside of your organizations if it's not fully open source. And for example, we did actually utilize that at Sandia last year to create a customized site for some internal projects. And yeah, finally, again, there's this kind of hold up impediment of this, needing to know how to design secure software and a pretty significant training burden for this minimum level of knowledge that I think that we might be able to address as a community in terms of what we consider to be sufficient for our different kinds of codes. Yeah, and with that, we have questions, discussion, whatever that's come up here. And if projects that are interested, you might just be curious to try it out on one of your projects and just kind of get your hands dirty and see what that process is like. You might find that to be a positive effort. So yeah, thank you very much.
Thank you all three very much for your presentation. And we do have a few questions, and then we'll be able to open it up more generally. So the first question is somebody commenting early in the webinar, you talked about the OpenSSF badging program website, sending reminders, and they were asking if that's a new thing. They said they've never gotten a reminder.
Well, you might only get a reminder if you don't have a passing badge. I don't have a passing badge on my project, so that might be why I get the reminder. If you have a project that has a passing badge, then they're probably not going to remind you.
All right, and then you talked a lot about this no secure design criteria, and they talk about a course to address that, but I'm wondering how specific the actual criteria is. Do you have to take that course, or is this just meant to give you an idea of the level of knowledge that's expected, or what? So are there other ways to satisfy this criteria?
I mean, technically speaking, they don't mandate that you take one of the courses that they mention. So I think it's on you and on your project for deciding how you satisfy that. But they mention a lot of courses, and the shortest course that they mention is that 18-hour course. So they're basically putting a very high bar for this. But I think by trying to throw a very wide blanket over a lot of projects that potentially are in positions that are really security critical as part of our open source ecosystem, right? That we have for the internet and for Linux distributions and so forth. I think that makes sense, but I think that for more narrow sets of software applications, we can probably, in good faith, and come up with some graded levels of training for specific issues that are applicable to our projects. Like I wish we could have like a menu item of areas that our project is involved in, right? Of course, core software itself, all that, getting rid of undefined behavior. But then, you mentioned like MPICH, right? A lot of our projects are distributing software binaries. Well, there's a big security issue there, right? If you're not careful about how you distribute binaries, man-in-the-middle attacks can basically put in fraudulent code and not even know it. So nobody can completely ignore all those things, I think, if we're going to be putting out software. So I think I don't know, I'm not sure what to do about it, but clearly I don't think everyone needs to take even the 18-hour course and provide pretty good levels of security for a lot of our projects that don't really have a lot of these vulnerabilities, right, associated with them. So that's my view.
So I'll note here, we've got Todd Gamblin on the line, I think, but the High Performance Software Foundation is a home for several scientific software projects and hopefully a growing number over time. And I saw something recently where the Linux Foundation is contemplating making satisfaction of at least the passing badge, OpenSSF badge, requirement for all Linux Foundation projects, which is HPSF is part of. And that might be an opportunity to raise this question of, is there a somewhat more graded approach possible for this security concern, which is understandable, but maybe overstated for many scientific software projects. But certainly we also have to recognize there's plenty of scientific software projects out there that are doing things that have fairly big risk surfaces. So yeah, we have to keep that in mind too.
I mean, also,
yeah.
I just want to mention that this is self-reported. So if you mandate everyone satisfy it, they're just going to check the box and then everyone's going to satisfy it. Because some things, they don't have automated checks for. Like, how do you have an automated check that someone knows secure software other than mandating courses and having certifications? That would do it, right?
Right.
But yeah, I'm curious to see how far they'll go with that.
So these are the questions that we've had online. There was also a long chat in the Zoom that I think is worth capturing, but there weren't really questions that I saw raised there. So I think we can open up for general questions and discussion from folks on the line. Please raise your hand if you want to speak. All right, not hearing too much. So let me ask the folks on the line, how many of you were aware of the OpenSSF badging before this webinar? Maybe you can just use the thumbs up reaction to express your thumbs up or thumbs down. There's probably not a thumbs down. Oh, somebody found the thumbs down button. So far, people don't seem to have a lot of prior awareness of OpenSSF. How many people would, now that you've heard something about it, would think it would be relevant for your project to try to look at what we've seen with the OpenSSF badging and consider adopting it? Nobody's going to fess up to that one. Yeah, okay, we've got somebody. And in the chat, Daniel says the community software facility at NCAR might be interested. Yeah. Something new, so he can't commit to what they're actually going to do yet. All right, very good. Well, I hope this webinar was useful. As I said, we'll have the recordings and the Q&A available soon. Please be sure to share it with your colleagues, and we'll be interested to revisit this topic down the road. And if you have some interesting experiences with the OpenSSF badging that you'd like to maybe present on a future webinar, definitely reach out to me. I'm David Bernholt at Oak Ridge National Laboratory. And with that, I think we've reached the end of our time. Thank you all very much for participating.
Thanks, everybody.
And a special thanks to our speakers.